Here, this 0 is just an example. It's just the common number, the easiest, like the simplest threshold that we can consider. Of course, you can change that threshold to other value. Okay, so and also you may either change the problem, in the opposite way. This 0 is like the lower bound, right? But you can impose an upper bound. Then if the actual y value y star is greater than an upper bound, then we won't observe the actual y star value. Instead, we just observe that upper bound. That will also work. All right, it's just symmetrical. Or you may impose both upper bound and lower bound in the same time. That also works. All right. All of them, basically the same framework, the same kind of the corner solution problem. So, but the 0 is the typical setting, the most standard setting. So we're going to focus on that. We just, fixed idea, just focus on 0. Okay? So just the actual y star, if it falls below 0, we will not observe the actual y star. We only observe 0. Right? But here, there's one distinction we need to be aware of, to distinguish this problem from the next, the other category of the model that we're going to introduce. For this corner solution model, for those observations whose actual y falls below this threshold of 0, do we observe that observation? We still observe that observation. All right, we still observe all the x values, all the precise x values for that observation. The only information is limited is the y value. All right, the y value, the actual y value, y star, we don't observe that. We only observe 0. But we still observe some information about the y value because we see 0. So we know that the true y star must be less than or equal to 0. That's still, useful information about the dependent variable for this particular observation. Right? And plus, we observe all the x values for that observation. All right, so in this sense, for this type of problem, the sample is still complete. All right, we don't miss any data observations. The sample is still a random sample that we draw from the general population. And each observation we randomly draw, we observe them. All right, all the x variables we observe. Okay, even for those censored observations, we observe all the x variables. And then for them, we observe y, the censored y, but that's still useful information, relevant information about y value. All right, so that's the feature of this type of model. So for the other type of model, which is called the truncated model, which we're going to introduce also in this topic, that's different. Then sometimes truncated model is for those data observations whose y value is below the threshold. Then you completely miss the whole observation. You don't observe anything about that particular observation. If that's the case, that's called truncated. All right, two different types of problems that we face, and we need to address them differently. Right? So here is all the observations you observe. Okay? The only thing that's limited is the y value. Right? If the true y value falls below that threshold, you only observe this corner the solution, this threshold. All right. Then for this type of model, how should we estimate that? Can we just use the usual linear regression, OLS, to estimate that? Obviously not, right? Because now that, OLS would, how does this model differ from OSS model? Just the y value, right? So the limited visibility of that true y value. If we knew all the true y value, then basically reduced to the usual linear regression problem, right? So that's the limited. The only difference is that now, if the true y value falls below the threshold, we only observe that threshold. That's only thing. Then certainly we cannot use the usual linear regression model to estimate that, by treating this 0 as the true value. Obviously that's wrong because that's not the true value, right? That's a censored value. So we have to do something different.
Is it same as building a linear regression model and then having another function that filters out its values? It's like two functions.
Use two functions.
It's just passing the data to two models or two functions.
That's your proposal way of estimating this, right?
That's my understanding of it.
Okay. So two models. Yeah, you could say that way, but the thing is, how do you know?
I mean, once I get the y predicted value.
Yes. I mean, yes, right. You can think of this way. Basically, for those observations whose actual value is above 0, right, you can use those actual value. But for those observations whose actual value is equal to 0, right, you're observing the data is equal to 0, then you have to model them differently, right? In that sense, yeah, you can think of it as a combination of two different models.
Yeah, I realized my mistake. I just noticed you.
No, but yeah, you know, the intuition is relevant. So later on we're gonna see, basically you still handle them, you know, like through two parts. Like I said, some observations, you observe the positive y. Then those observations, you know the positive y is the precise y, the actual y. Right, so then basically that one you estimate that using the, you know, you don't really estimate them using the OLS, but essentially for those observations, you know, the actual y is just like the regular y. But for another set of observations whose observed y is 0, then you know that those zeros do not reflect the actual y, but instead they indicate that the actual y is below that threshold. So then you utilize that information to write out the likelihood function. All right, actually this model is another example of a nonlinear model, and we're going to use MLE, maximum likelihood estimation, to estimate that as well. All right, so let's look at how to do that. So you see, for this setup, what we can do is that we can write out the probability of y equal to 0 as this. It's the same as we derived that probability of success in binary response model. Right here, this probability of y equal to 0 is equal to 1. Based on the model setup, you can just write that, derive that probability. So the observed y equal to 0 is essentially equivalent to the actual y star being less than or equal to 0. Right? The actual y star being less than or equal to 0 because the actual y star is modeled this way. So essentially, it means this whole thing, the linear combination between x and the beta plus this error term is less than or equal to 0. And then you just do the linear algebra, the transformation. It's equivalent to the error term is less than or equal to minus the x beta linear combination. Right? This is equivalent. So this basically y star is x beta plus u less than 0. So then it's equivalent to u less than minus x beta. All right, again, x beta is a vectorized expression. Basically, this x beta simply means this linear combination. Okay, beta 1 times x1 plus beta 2 times x2, plus all the way to beta k times xk. All right, this is just a shorthand of this sum. All right, again, here this u is our regular usual error term. So u is considered as a random variable. Okay, and then this random variable, we assume that to follow this normal distribution. Now, of course, you can impose a different distributional assumption, and that will lead to a different expression for this probability. But usually, the standard model, we're going to just assume that this u follows the usual normal distribution. Normal distribution standard at 0, and we have this variance as an unknown parameter. This sigma square is an unknown parameter, also to be estimated from the data. All right, so that's the sigma square. So in this model, basically we have what are the unknown parameters? All the betas as usual, plus the sigma square. All right, so so we have this additional unknown parameter to estimate. All right, so anyway, back to this setting. So then this u, this random variable less than this x beta. And then u, because u follows this distribution, right? So then we can just write it this way. We divided that u by the sigma square, basically to normalize that. So then the u over sigma will become like a random variable following standard normal distribution. Standard normal distribution has mean 0 and variance equal to 1. All right, so that's what we have here. And then basically, this phi is the CDF function of the standard normal distribution. All right, CDF, again, what is CDF? CDF simply measures the probability of this focal random variable being less than or equal to a certain value. Right?
I'm confused why we're dividing by sigma.
It's just to normalize that, because this U follows this random variable, follow this normal distribution with variance equal to the sigma squared. So then we divide by sigma squared, then U over sigma squared will be a random variable for the normal distribution with mean 0 and variance 1. So that's just the standard normal distribution. It's just a mathematical transformation. It's just equivalent. All right, because standard normal distribution, we know everything about that. We know the CDF, we know the PDF, it's just standard, right? If you have a sigma square which is unknown, then you introduce this additional parameter into this CDF function. All right. So this is the standard normal distribution, and because of the symmetry, so this one is equal to this. All right, because negative, we draw that, right? So you normal distribution, negative means the probability less than that, and then it's the same as the probability of greater than the the positive value. All right, so again, that's just the usual derivation, just deriving this probability of the actual y being 0, right, following our model setup. All right, and then what you can do is that this is y equal to 0, right? Then for y greater than 0, what can we do? Like we just said, for y, in the case of y greater than 0, actually, we know the actual y. We know the precise y. So no need to derive something like that. All right, because we know that. So that's just the usual model. So we can write this one. This is actually the likelihood for those y that are greater than 0. So that's just the likelihood. So for continuous value, for continuous value, right? So the likelihood, is actually you can just use that density function, the PDF. So that's why for you can think of the likelihood of observing a positive y is simply equal to the probability, right, or the likelihood of this u equal to y minus this one, right? Because if I observe a positive y, I actually observe the actual y star, right, which is just equal to the value I observed, the y value I observed. And then this y value is modeled as equal to this linear combination plus this u. So it's just, the likelihood of observing that y is simply equal to the likelihood of having this u value equal to this y minus this linear combination. Right? And then the u, we know that the u follows this normal distribution. So it's just the likelihood simply becomes the PDF of a standard normal distribution substituted in this value. All right, anyway, this is just the derivation of these two parts. All right, for those observations that y is actually equal to 0, that's the likelihood function. And then for those values that y is positive, that's the likelihood function. So then what we can do is just to put them together. Write out the entire likelihood, the overall likelihood function for all the data that we observe. How to do that? Just like what we said, right? We break that into two parts. For those observations in our data whose y is positive, we use this one as the likelihood function. All right? For those, for those observations in our data, right, whose y is positive, then we use this one as the likelihood function because we observe the actual precise y, right? And the likelihood for us to observe that is this much. So they enter here. All right, like that. This part is exactly this one. That's the likelihood function for that part of observations. Those observations whose actual y is positive. Then for those observations whose actual y is 0, what's the likelihood? This one. You see the difference? Right? So for those observations, the actual y is 0, the likelihood is equal to the precise y being less than or equal to 0. It's not like being exactly equal to 0. Right? The precise y is less than, and taking any value less than or equal to 0 will translate to observing the observed y being equal to 0. So that's why for those observations you observe a 0 in the data, the likelihood is equal to this. As we derive. This clear? The two parts, why they are different and how they are different. That clear?
The very last line, the conditional y given x, y, is there 1 over sigma outside of the?
Yeah, this one is, yeah.
How does it?
This just a normalization. Just a normalization. If you do this, change of variable, right? You have to take that out. Yeah, in deriving this, likelihood, you have a change of variable that, that value has to be, that coefficient has to be taken out. All right, so this is the full likelihood. This is, this is the likelihood for one observation. Okay, but depending on whether that which category this observation falls into, either it's one of the observations whose actual y is positive, or whose observed y is positive, or those observations whose observed y is 0, we use different expression for the likelihood. And then what we do basically, we just combine all the likelihood, all the likelihood function from all observations, right? And of course we can do this log likelihood. The log likelihood is just the likelihood function take a logarithm. Then the reason we do log likelihood is then instead of doing all the products, all the multiplications, right? When you take a logarithm, those products becomes what? Sums. Yeah. So you have a product of all the likelihoods, right? But you take a logarithm, then basically it becomes sum of all the log likelihoods. That's just like a usual transformation we do. Then it's easier to handle, mathematically. Instead of, usually we want to do sum is easier to do than products. And then, it preserves the monotonicity, right? So, eventually we want to maximize the original likelihood function. But maximizing the original likelihood function is equivalent to maximizing the log likelihood function. That's equivalent, right? Because the logarithm preserves the monotonicity, preserve the if it's increasing, you preserve the increasing property. So that's equivalent. So that's why it's often that's what we often do, right? We say it's a maximum likelihood estimation. We maximize the likelihood, but in practice we simply just maximize the log likelihood because the solution is equivalent. The solution will be the same. All right, so that's what we do. So we take the logarithm and then we add them together. So again, this part is all the observations whose observed y is equal to 0. And this part is all the observations whose observed y is greater than 0. All right, so then this is similar to how we derive the likelihood function for this binary response model. Binary response model, we also have two categories. One category is those observations whose observed y is 0, right? And the other part is those observations whose observed y is 1. So then we derive their likelihood separately, and then we combine them together to form the overall likelihood function. Here, that's the same. All right, but here is the two parts are different. The one part is those observations whose observed y is positive. The other part is those observations whose observed y is 0. Okay? And then the estimation approach is the same. We numerically search for what? We say maximum likelihood estimation. The estimation for what? What is changing?
Beta.
What is the unknown?
Beta.
Beta. Yeah, all the parameters, right? All the beta, the unknown parameters. Those are the unknown variables. Okay, so then we search for the values of those betas, right? That will maximize the log likelihood function. Right, but like I said here, pay attention here. All the unknowns in this model, in addition to usual betas, we also have this sigma squared, this additional parameter, which is the variance of this distribution, normal distribution of the error. All right. Actually, one quick question for you guys to think about that. I cannot to further confuse you, but think about that. We have this binary response model, have similar setup. But do you recall what distribution do we assume for that error term in binary response model, in logic or probing model? You still recall? Also, normal for probing model, all right, logic model would assume that it's a logistic distribution, it's different. So probing model. For probing model, the error term is what? Follow normal distribution, right? But one normal distribution, what's the mean? 0. What's the variance? 1. All right, for probing model, we actually assume the error term follows standard normal distribution. We actually didn't allow that variance to take a different value other than 1. So we didn't allow that variance to be a free parameter to be estimated from the data. Now think about that. Why here we do this? Why we didn't do that in probing model? Here we allow this variance to be a free parameter to be estimated from the data. But why we didn't do that with the probing model? In other words, why can we do that here? Or why couldn't we do that with probing model? Yeah, this is actually interesting. When I first learned about that, that's the question I had, and thought about that and figured that out to you. I feel like that's very reasonable.
Isn't probability contained between 0 and 1? So that way you don't need anything more.
It's not that you don't need, but in the probing model, you cannot identify that variance from the data. Why? Because you have two limited information. The y is either 0 or 1. Right? You see, the sigma square is identified by what? The entire distribution, how widely this distribution spreads. Right? But when it's the probing model, you have very limited information. You only observe 0 and the y. And that information can only help you identify the probability of this actual y either above the threshold or below threshold. That's it. So that information is only enough for you to identify the mean rather than the spread out. So no way for you will be able to identify this variance from the binary response data that you have. So that's why no way you can estimate, you can identify that sigma squared variance as a free parameter in the binary response data. All right, so that's why the only thing you do, the best you can do, just to fix that to 1. But here, why can we do so? Why are we able to estimate this sigma square as a free parameter? Why?
So it follows a continuous distribution. It's not
exactly, right? Now for all those values that's greater than 0, you observe the precise value. So sort of you observe part of the full distribution. Right? The only part you don't observe is those values that's below 0. But for those values, it's above 0, you observe the precise distribution. You can think of that you observe half of the actual distribution. And that half is enough because the normal distribution is assumed to be symmetric. So that half is enough for you to identify the variance of that ratio. So that's why with this corner solution model setup, you are able to estimate, you are able to identify this variance of the error term as a free parameter. See, that's the difference. So make sure, you understand that. All right. All right, so that's it. All right, so this is, this model setup, this setup is what we usually refer to as the Tobin model. All right, Tobin model, named after this famous statistician Tobin. Tobin. For those of you who specialize in finance, you should be familiar with this name, right? Tobin's Q. That's like a common measure used in measuring this finance, the performance. So the same Tobin. All right, so it's Tobin. So Tobin model. Tobin model simply just refer to those corner solution model. And the standard Tobin model setting, the threshold is 0. It's just like that. All right, if the actual y is positive, you observe the actual y. If the actual y is below 0, you observe 0. All right, it's called Tobin model. All right, and then that's how the model is set up, and that's how the model is estimated. All right, and now the usual estimation. All right, now again, you just run the MLE, numerically search for the beta and the sigma value to maximize this likelihood function. And then after that estimation, we found the beta, right? The R will receive, return, will show you all the estimated beta value, and together with that sigma squared. Then what can we do? Next thing is after we obtain the estimation, we want to interpret, right? So then what do those beta values mean? So again, how do we interpret what sort of effect are we interested in measuring? The usual marginal effect or partial effect. Again, here, how do we define the usual marginal effect and partial effect? One unit change in the x variable of interest, how much will that change the expected value of y? Right? The usual definition. But now, here is the tricky part. What is the expected value of y? Or what expected value are we interested in measuring? Yeah, here is the trickiest part. So what are we interested in measuring? Here, what we are interested in measuring for this corner solution model, what we are interested in measuring is that the expected value of observed one. All right? Because the corner solution model, for example, think about the consumption decision. You can never really have the actual y. The actual y doesn't exist. Right? The actual y star, the latent y, could be negative. But for the consumption decision, the negative consumption doesn't even exist, never actually exists. So it's only like a hypothetical value. So what really matters is the observed y. Right? So if it's a corner solution, then what matters is just this corner solution is 0. That's what matters. All right? So in this sense, what we are interested in is the expected value of the observed y. That's what matters. That's what exists for those type of problems. All right, if a consumer just consumes the consumption value is 0, then it's just 0. That's the 0 that matters. All right, we want to know the expected value of the observed y. Okay, so that's what we are interested in. All right, so what we are interested in is the expected value of this y without a star. And then we want to see that how much one unit change in x will lead to change in this value. Now here, the tricky part is that how to measure this one, expected value of y, right, given the x values. That's complicated because here, the expected value of y is determined by this. Right? If y is positive, the expected value of y is that equal to that positive value. But if y is 0, this y star is less than 0, then the expected y, the observed y is just 0. So then what is the expected value of observed y? That derivation is a little bit complex. All right, so you need to use the conditional distribution. Basically, conditional on the fact that the y star, the latent y, is positive, then the actual y is, the observed y is just equal to y star. But conditional on the fact that the latent y is negative, then the observed y is just 0. So then you do the expectation. All right, so a little bit complex. So we'll skip on that, but that's it. After playing with all the conditional distribution, conditional expectation, you should be able to derive that as this. Yeah. But what makes more sense is the next one. How do we derive the marginal effect? We can derive the marginal effect by taking the usual partial derivative of this expected value of y with respect to a particular x variable of interest. Right? Again, this measures how much one unit of interest in x will affect the expected value of y. Now, we can write this this partial effect, this partial derivative, as this. And this expression actually makes a lot of sense. All right, so make sure you understand that. You see, we can decompose this partial derivative into two parts. basically applying the usual chain rule. Two parts. One part is what? You see, the partial derivative of the probability of the observed y being a positive value as a result of the change in x value. Okay, times the expected value of y conditional on the fact that y is positive. All right, what does this mean? This means that this first term measures the effect of when x changed by 1 unit, how much the probability of the observed y becomes positive, that how much that probability will change. Right? That's what's measured by the first part. Then the second part is what? You see, this is like the given that the y is already positive. So the probability, under the probability that the observed y is positive, then how much this change in the x variable's value will affect the expected value of y, conditional on that it's positive. All right, so in this sense, why this is important? So basically, intuitively, you can think of this. What is the effect of change in this focal x variable's value on the expected value of observed y? We can decompose that into two parts. One part is what? X variable change. It will affect the probability of the observed y becoming positive. Right? Going beyond that threshold. That's one part of the effect. Another part of it is that it will increase probability, the expected value of that positive y once it becomes positive. You see two parts, because the observed y can be either 0 or positive. Right? So when you increase the value of this x variable, you actually increase the probability of you observing a positive y rather than a 0. That's the first effect. Second effect is that, if I observe a positive y value, then if x variable changes, then the actual value I observe will also change. Right? So the second effect is sort of like the usual marginal effect. When x variable changes, the y value will change. But here, this effect is present only when the y is positive, is already positive. Then you observe a change in that positive y's value. But if the original y is below 0, then the observed y will not change. Right? Even if the latent y, below 0, its value is increased. But if it's still below 0, the observed y, the value will not change. It will still be 0. Right? So in that sense, how will that affect that part of the value? It only affects through the fact that if x variable's value increases or decreases, the probability of the latent y goes above this threshold 0 will change. You see, that's why there are two parts of effect. All right, corresponding to the two scenarios, right? If the latent y is below 0, then how you change this x variable will only affect the chance of that latent y eventually goes beyond this threshold 0. But if the latent y is already above 0, then changing x will lead to change in the observed value of y. And that's the usual effect. So, but the overall partial effect actually is a combination of these two parts. All right, so that's the complication. That's the complication beyond the usual linear regression set. Question?
Yeah, so does that mean that when you're trying to interpret these effects,
Yes.
You have to look at what the predicted y value is in order to interpret it correctly? So like if it's predicting a positive y value, you're basically interpreting it like a standard multiple linear regression. And then if it's predicting a negative y value, then you have to look at the odds.
Yeah, but here what we are talking about is overall, the overall effect in general. So that's why it's a combination of both possibilities.
Okay.
All right, so that's why it's two parts added together. All right. So that's the thing. Another thing, take a look at the derived expression. This is the final, this is the mass is complex, right? And you need to pass in this conditional expectation, those things, and combine and do the derivation. Of course, you can also do the derivation directly from this expression. Basically, then you directly take a partial derivative of this expression with respect to x. That's also fine. You can derive from this one, or you can derive from this one. Anyway, but math is a bit complex. But after the derivation, after all the kind of the organization, eventually the result is neat. So this is the marginal effect. Take a look at that. What does that imply? This phi is what? CDF of a standard normal distribution. How does a CDF of standard normal distribution look? Still remember? CDF of standard normal distribution, how does it look? What's its shape?
Sigmoid.
Exactly, it's an S shape. All right, S shape. CDF is the cumulative, right? The bell curve is the PDF, is the density function. CDF is cumulative, it's S shape. Now S shape, the value is bounded between 0 and 1. Now think about it. What does that imply? So let's say X value is extremely small. Okay, this entire thing, x beta over sigma, entire thing within the parenthesis is negative, converge to negative infinity. Then what does this sigma of that converge to?
0.
0. Okay, 0. What does that imply for this partial effect?
Small.
0. Right, so when x is negative, the partial effect converges to 0. What does that mean? Let's assume that this beta j, this beta coefficient in front of the focal x variable is positive. Then what does that mean?
It has no effect.
It's positive, right? So then when this focal x variable increases, it will increase y star, right? As the usual linear setting. When x is this focal, let's say focal x variable is x1. So let's say beta 1 is positive. So then x1 increases, it will increase y star. But why the partial effect is 0, is almost 0? Why? Because at that time, again, x is negative, it's very negative, right? So close to negative infinity. Very negative. Then most likely this y star will be negative, will fall below the threshold. So no chance you will actually observe a change in the y value because the observed y will always be 0. So even if x increases a little bit, it doesn't really change the observed y because the observed y will always be 0. That's why the marginal effect is 0. It's almost 0. You see, this part is correspond to that because the value falls below the threshold. So you will never observe any change in the observed y because the observed y is always 0. You see, that's how it's different from this standard linear regression setting. Because standard linear regression setting, the marginal effect will always be equal to the beta coefficient, right? Because whenever you increase the x by 1 unit, the y value will be increased by beta. But here it's not. You see, it depends on the value of x. Because it will affect the probability that you can observe the positive y. And then as a result, you can observe change in that y value. If you cannot observe a positive y, even if the negative y star changes, the value changes, the value increases, but you won't observe that. In the observed y, there's no change at all because it's always 0. So that's why when x is extremely negative, the marginal effect is 0. Now, what if x is extremely positive? Then sigma of a extremely positive value is what? Close to 1. And then the marginal effect is close to what? Beta j itself. And then it restores to the usual setting. You see, now the marginal effect is when x is very positive. So you are almost for sure to always observe the positive y, the actual y star. Then, the marginal effect is just simply the same as the marginal effect from a usual linear regression setting, which is just equal to the beta coefficient itself. Those-
So can you think of it like, since it's on the S curve, and then the positive part of the S curve will approach some constant,
Yes.
and then the left half will approach some zero that maps to the marginal effects.
Exactly. So the marginal effect, essentially, you can say it's bounded between 0 and the beta j itself. Right, but it's changing with the value of x variable itself. All right, so again, yeah, understand this why this is the case. All right, so this is the Toby model setup. Again, just the complications that is the censorship, at below at 0. It's reasonable in many sense, but there's one major limitation of this model, which is what? Because of the setup, the two things are bonded together, are linked together. The probability of y greater than 0 and the expected value of y conditional on that it's greater than 0. These two things are closely linked together due to the setup. In other words, when some x variable change, right, it will change both. It will change the probability of we observing a positive y, and it will also change the expected value of a positive y. These two will, because of the design, because of the setup, they are the same thing. So they will always be changed together. So, but in reality, this may not always be the case. In some scenario, these two things are separate, right? The probability of you observing a positive y versus the expected value of y, given that it's positive, may change differently as a certain x variable changes. So that's why a more general model, this will not, if they are changing differently, then they will not be able to capture by, be able to address well by this standard problem model setting. So that's why more general model, you need to generalize that, basically break that type. All right, you come up with a two-part model the two parts separately. The probability of y becoming positive, we model that separately as one function of all x variables. And then condition on given that it's positive, the expected value of y, we model that as a separate function of all x variables. That's more general setup. But of course, it introduces more complexity. So we'll just stay with this standard Toby model. All right, so that's just the Toby model. All right, so that actually corresponds to this so-called corner solution model. But there is another type of model called a censored model. All right, a lot of people, oftentimes people actually, use the word interchangeably. They will treat this so-called censored model that we introduced here to describe Toby model. All right, because of its similarity, it's very similar. Basically, the whole setup is almost the same. What's the difference? The only difference is that in the so-called censored model, what matters is this latent y, rather than the observed y. All right, but in the so-called corner solution model, the difference is what matters is the observed y. Because the observed y is a corner solution, just like we said, the consumption volume. The consumption volume, 0 is 0. Right, so what matters is that 0. Economically, all the prediction, all the analysis, what matters is the actual consumption value we can observe is 0. Although, you can think of the intention, right? This individual's intention, the theoretical, hypothetical optimal consumption value would be negative. But he can never really consume a negative volume. So that's why what matters is the actual observed the consumption value, which is the corner solution 0. So for corner solution model, what matters is the observed one. But there's another case in this censored model setting. What matters is this latent one. Simply the latent one is what at work actually. But the observed one is simply just due to some censorship in our data collection. For example, when we do survey, right, we ask about your income. Survey has several categories, right? Income greater than certain level, right? 100,000. Or less than certain value, less than say 1,000. Then people will just choose those categories. And then you only observe the income being is a value greater than the upper bound or a value lower than the lower bound. You don't really observe the actual value. Right? But in those contexts, what really matters That's the latent y star, the precise y star, the latent y star, right? Because income, goes beyond that threshold. But still, we are interested in the y star. That's at work. That's affecting all our, analysis, all the effects that we are measuring. All right. So this is how this so-called censored model differs from the corner solution model. Other than that, it's exactly the same. The whole setup is exactly the same. The only difference is that in the so-called corner solution model, what matters eventually when we derive the so-called the partial effect, what matters is the expected value of observed y. But in the censored model, what matters is that the expected value of the latent y star. You see, that's why we want to make this distinction. But that's also why many people do not make this distinction, because essentially the model setup is the same. The only difference is after the estimation, when you try to interpret the marginal effect or the partial effect, what you are measuring will be different. All right. Again, for corner solution model, the marginal effect is measuring how this x variables change will affect the expected value of observed y. All right. But in the censored model, the marginal effect is defined as how the value in x variable, the change in x variable's value will affect the expected value of the latent y. Now, ask you, which one is simpler? Which one is simpler? Measuring the impact on the expected value of observed y, or measuring the effect on the expected value of latent y? Which measure is simpler? Exactly, latent y. Actually, latent y makes our life much simpler, much easier. So latent y, what's the effect? What's the marginal effect? Very simple answer, just the beta coefficient. Right? Because if we want to measure the effect of a certain x variable's change on the expected value of latent y, then the effect is just the same as the marginal effect in the usual linear regression, which is measured just by the beta coefficient. All right, so that's why if we are dealing with the second case, the censored model, where we are really interested in the effect on the expected value of the latent y, then after the estimation, the partial effect, that calculation is straightforward. We don't need to do any calculation, just the beta coefficient simply measures the partial effect. The same as usual linear regression. Is that clear? So the model setup is still the same, and the estimations are still the same, because the data we observe is still censored like that. We do not really observe those negative latent y. We do not observe. But when we do the interpretation, because what we are interested in is the effect of latent y in censored model. So then the marginal effect, the partial effect, is simply measured by beta. All right, that's the censored model. Again, it's the same as the corner solution model. The only difference is how the measurement of this marginal effect. Okay, so and the censored model essentially is much simpler. All right. Okay, finally, let's talk about this truncated model, the third model. Again, very similar, very closely related, but that's different. Truncated model. What do we mean by truncated model? That goes back to my earlier comment. Corner solution model, the censored model, the Toby model, the setting. Do we observe all the data? Do we observe all the observations? Yes, we do observe all the observations, regardless of the value of the y. All right, even if the y, the latent y, is negative, we still observe those observations. We observe the precise value of all the x variables. And we also observe the y outcome, just that the y outcome is 0, is observed as 0. So in that sense, the data sample we observe is still complete. All right, so it's still a complete random sample from the population. We do not run into the so-called selection problem. The sample is still complete random sample drawn from the population. But there is another type of problem, another type of data that we may face. This is called a truncated model. Truncated model is that observation will be missing if the dependent variable falls beyond the threshold. All right. So in the same setting, for example, if let's use the 0 as the setting as the threshold, then if for those observations, if the y falls below 0, then we do not observe the observation at all. Then the observation will be missing from our data. We do not observe all the x variables, not to mention the y variable. So all the observations that we observe in the data are those observations whose y star is greater than 0. If that's the case, that's a truncated problem. All right, and that's very common as well, depending on your data collection mechanism. Okay, very common that you will run into those truncated problems. All right, so all the data you have only contains those observations whose dependent variable y star is greater than a certain threshold. Those observations whose dependent variable falls below that threshold, you don't observe those observations. If that's the case, what's the problem? That's actually more complex problem, because now you no longer have a random sample from the general population. Right? The sample is selected, so you run into so-called the selection bias, the selection problem. So the sample is selected. So everything you see are only those observations that satisfy a certain condition. Okay? The sample is selected. So that's the problem. So then how to do that? Then you need to correct for the selection bias. So that's the model. That's how we can handle that type of model. So the model setup is like that, right? So I mean the basic idea is the same. You have this y, right? Again, it's usual linear combination, usual like that. But the problem is that for those observations, if y is, again, this one you can either use the upper bound or use the lower bound or use both. That's all the same. All right, you just with some simple adjustment, you can adapt to all those different cases. You have a lower bound. Then for y falls below that lower bound, you don't observe that observation. Or you can set up an upper bound, right? For y goes beyond that upper bound, you don't observe the observation. Or you can have both lower bound and upper bound. For y values falls outside of that range, then you don't observe the observation. All those can be equally handled. So here, let's just say we have an upper bound. For all the y values, for all the observations whose y value is greater than that upper bound, then that observation will be missing. If that's the case, how can we estimate the model? Again, we still use maximum likelihood estimation, but we need to write the likelihood accordingly. We need to write the likelihood properly. All right. So the likelihood need to be written like that. We need to adjust for the fact that we observe this observation is because the y value is less than this threshold. All right, so the likelihood now becomes a conditional probability. So this one, in the numerator, that's the usual likelihood for the y value that you observe. Right, so what's the likelihood of observe that particular y value based on this linear setup, this model setup. This numerator is the usual setup. What is this one? Basically usual PDF, right? Usual the density function of this normal distribution, right? Substituting this value, the y minus this one. So that's the usual PDF for this error term. All right, so that's the usual density function. But what's different is that now this likelihood needs to be divided by this condition. This condition is that the fact that we observe this observation is because this observation's y value is less than the threshold. Because otherwise we wouldn't be observing this observation. So the likelihood need to be normalized by that probability. So that's why we divide that by this probability. The probability of y value falls below this threshold. Again, this big F is the CDF function. All right, the CDF function, again, CDF function measures the probability of this focal random variable, which here is the error term, being less than, this particular, the particular cutoff. Question?
I guess if the whole point of the truncated model is that neither the x or the y is recorded if it's past the threshold, how would we know, like, the distribution of the missing values?
It's not like the distribution of the missing value, it's the probability that you can observe this one. You adjust for the probability. You are observing this one. So that means, that's why we have to add this probability. Right? So we observe this observation only because its value is less than this threshold.
But if the value isn't recorded, how would we know the probability of a value being not recorded?
Yeah, that's a good question, but here you are deriving this based on the assumption of this error term. All right, so this probability is derived based on the assumption of error. So you still believe that the error term follows a certain distribution. Yeah, of course, if you think that's not a reasonable distribution, that's a different story. Then you need to correct for that distribution. But of course, you can assume a different distribution, but usually a known distribution. So with a known distribution, still you can do the same thing, but just this CDF will be different rather than the CDF of normal, but the CDF of another distribution. Yeah, that's good thinking. But you can adjust for the distribution assumption. But the setup is still the same. All right, so that's the, after that correction, actually that is the likelihood that we can use. Again, this likelihood is based on the observed data. But we just correct for the fact that the chance of observing this particular observation is this much. It's because it's equal to the chance that the outcome variable, the y, is actually below that threshold, that cutoff. We adjust for that. So that's the, the so-called selection bias adjustment. Adjust for that selection bias. And then with that, we just write, put all the likelihood. This is the likelihood for a particular observation. And we again, as usual, we just put all the likelihood for all the observations, just multiply them together. And then if we take the logarithm, then it's just the sum. And then we maximize that. Okay, search for the beta value and the sigma square value to maximize that likelihood. And then we're going to find the estimated value. All right, then the next question is after the estimation, after finding the estimated beta values, how should we interpret that? Again, the usual partial effect. But now here, what is the partial effect? What value is of interest here?
Beta.
Still the original value. All right, this y value. And what is the partial effect? Again, very simple. If we are interested in the y value, the effect on the expected value of y, actually, the partial effect is just beta. All right, because although those values are missing, but still, what we are interested in is still the original value. So then what we are trying to infer is still the impact of changing x variable on the expected value of that y. So then the partial effect is just the same as the usual linear regression. Just the beta coefficient itself directly measures the partial effect. All right, so for those type of models, the interpretation of partial effect is actually simple. And what's the important is that when you estimate the beta values, you have to correct for that selection bias. All right. And these are the package, the R package that we can use to do the model. So we're gonna do that demonstration. For that question, for the second part of the homework question, we're a little bit behind the schedule, so I'm gonna postpone the deadline of the second homework. All right, so to give you more time, probably till next Wednesday or even next Thursday, I'll send out an announcement on camera. All right, so but the second part of the homework is actually very simple. It's only a few tasks, and basically we just try to run this truncated model and make some predictions. The key thing is for you to see that how those values will be different, right? If we don't account for those variations. Now, the one question I have for you to think about, we're gonna demonstrate the next class is that think about that for this type of truncated model, if we ignore the selection problem, how will the estimated value of beta differ? How will the estimated value of beta be biased? In what direction?
Both of them have the same rate.
All right, something for you to think about. Will we end up overestimating or underestimating the beta value if we ignore those types of selection problems?
Doesn't matter.
This is something that you should be able to figure out based on the setup. All right, it's something that I'll ask
guess.
you, and something that we'll actually see, in the data, whether the actual result
Dark weeks, whatever is